Morning, everyone. This is Mr. Trusino. I hope you had a very wonderful spring break. All right. I hope you are also keeping yourself safe. All right. Also for your family. All right. Today will be our first day of online learning. Okay. So before we begin with that, let's go over the online procedures. All right. For our mutual safety. Um, All right, here it is. All right, so distance learning safety. This material is readily available from the PGCPS portal. So should you need any more clarifications, or if you would like to look more, all right, into details, you can definitely access it over there. I think I also put up a link on our Google Classroom. I'm not sure. We'll definitely go over that, okay, with my with the Google Docs. I've actually put up along with this particular lesson. That is where we'll be discussing our online discussion. All right. So distance learning safety. Please be reminded that the PGCPS administrative procedures regarding appropriate use of technology, social media, and email continue to apply to our online instruction. In addition, this session may not be recorded without the instructor's consent. Let's focus on this particular statement. Now, this is a pre-recorded video, all right? So obviously, um, this particular statement is not exactly applicable, all right? So we'll just have to understand this as the video cannot be shared without the instructor's consent. So instead of thinking it as it cannot be recorded without my consent, we will think of it as it cannot be shared without my consent. Of course, you are free to share the content, all right, but you'll have to secure permission from me first, all right, because we have to, of course, follow the distance learning safety protocols. All right. So as I mentioned earlier, description of applicable procedures is provided online in the Student Rights and Responsibilities Handbook. Thank you for your cooperation. Definitely, thank you. Now I think we are ready for our lesson. Okay, so let's now access that file that we need to go over. All right, so here we go. Linear versus exponential functions. This file, of course, will be uploaded into the Google Classroom so that you may read it. You may read it before listening to the recording, or you may read it after if you need to clarify some things. So linear versus exponential functions. All right, so we're going to discuss differences, all right, and how to recognize one from the other. Okay, so before we actually delve deep into linear and exponential functions, let us go over the succeeding number series. I think this will be a good content for us to get a good understanding of what we actually need to look for. Aha, all right, so here are our four numbers. All right, so for the first one, we have -5, -1, 3, and 7. As the questions asks, all right, can you determine what number comes next? So what number does come after 7? Number 2, we have 2, 6, 18, and 54. Okay, so what number would come after 54 if it will follow the same pattern? Number 3, we have 10, 37 fourths, 17 halves, 31 fourths. Ha! Fractions, right? Not the most likable set of numbers, right? But definitely the pattern is there. And finally, we have negative 1,400, negative 160, and 64. So if this pattern continues, what number do you think would come after 64? So I'm pretty sure that a lot of you will definitely be able to figure out the answers eventually. So if you need more time, you may pause the video, solve it on your own, and then you can unpause so that you can check your answers with the answers I'm going to show at the next slide. So I'll give you time. I'll give you 2 seconds before I touch again. That should give you time to pause it. Okay. I think that should be enough time for you to have paused the video or unpaused it. Right. So now let's go for the big reveal. Right. What are the answers for these 4 numbers? All right. So for question number 1, the answer is 11. For number 2, it's 162. For number 3, it's 7. For number 4, it's negative 128 over 5 or negative 25.6. Right? Did you get the same answers? I hope you do. All right, so now let's try to see. All right, let's try to see what the patterns are. All right, just to see whether everyone figured it out. And for those who did not figure it out, which ones were they confused with? For number 1, it says here the next number is obtained by adding 4 to the previous number. Let's check that. Negative 5 plus 4, oh, that is negative 1. Negative 1 plus 4 is 3. Okay, that checks out. 3 plus 4 is 7. Aha. So, if the pattern does continue, 7 plus 4, that indeed gives me 11. All right, so therefore, 11 is really the answer for number 1. Great. Now we go to number 2. We have 2. All right. Oh, what is the pattern, by the way? So according to the blue ink, the next number is obtained by multiplying 3 to the previous number. So if we multiply 2 by 3, yeah, we do get 6. 6 times 3, yes, it is 18. 18 times 54, 18 times 3 is 54, yes. And finally, 54 times 3, 162, yes, all right. That does make sense. All right. Number 3, all right, 10, 37 fourths, 17 halves, 31 fourths, and 7. The next number is obtained by subtracting 3 fourths to the previous number. All right. So since not all of us are fans of fractions, right, let's try to go over the solution for number 3. All right, here we go. Here we go, people. All right, so we began with 10. All right, it was followed by 37 over 4. It's followed by 17 halves. All right, followed by 31 over 4. And then we're missing the 5th number. Okay, so let's try to see. The problem with this one is that the fractions are not similar. They all have different denominators. 10 being a whole number, so its denominator is understood to be 1. So the thing is, we need to maybe convert each fraction so that all denominators are 4, which is the LCD. 37/4 and 31/4 already have 4 as their denominators, so we don't have to do anything with them. 10/1. So how do we convert this fraction so that its denominator will be a 4? Aha, that's not the problem. Okay, to do that, all we have to do is multiply 4 to both 1 and 10. Okay, that will make the denominator 4 because 4 times 1 is 4. So let's try to do that. 4 times 10 is 40. 4 times 1 is 4. Aha! There we have 40/4. Yes, 40 divided by 4 is indeed 10. All right. We'll now do the same process for 17/2. In this case, for 17/2, all we need to multiply 2 to become 4 is just 2. So let's just multiply 2 to both numerator and denominator. 17 times 2 is 34. And 2 times 2 is 4. Aha! There we have it. All right, so now all of them are similar fractions, right? Having a denominator of 4. So let's now try to see whether we can determine a pattern among the numbers. All right, so notice the numerators actually follow a particular pattern. Notice 40, 37, 34, and 31, all right, has a pattern of becoming 3 less than the previous term, all right? So therefore, the pattern that can be achieved from this one, all right, can be subtracting 3 from the numerator. But because this is a fraction in nature, to subtract 3 from the numerator, we actually have to subtract it by a fraction of 3/4, right? Because otherwise, we'll have to convert the 3 as a fraction, all right? So to make it easy for us to easily subtract 3 from the numerator, we have to make the number we are subtracting also a fraction of denominator 4. In this case, 3/4. Right? So we subtract 3/4. 40/4 minus 3/4 is indeed 37/4. We subtract by 3/4 again. This gives me 34/4. Yes, that makes sense. We subtract by 3/4 again. That does become 31/4. So if we subtract by 3/4 again, so 31 minus 3 is 28/4. Now, 28/4, all right, actually is a whole number. 28 can be divided by 4. 28/4 is simply 7. Okay, and thus, our answer, the fifth digit in this particular expression, should be a 7. All right, let's go check whether it is indeed, aha, yes, it is 7. All right, great. Now to number 4. Number 4 is a bit tricky. -1,400, -160, and 64. Now, looking at the pattern, looking at the set of numbers, we notice that it alternates positive and negative. The only way this is going to work is if we multiply or divide by a negative number. Okay, if we keep adding by a positive number, the resulting digits or the resulting answer will not be fluctuating between a positive and a negative answer. All right? Similarly, the same is true if we subtract, because subtracting is just adding by a negative number. Thus, the only way to be able to achieve this particular pattern is to multiply or divide by a negative number. In this case, after trying out some particular numbers, we determine that the next number is obtained by dividing negative 2.5 to the previous number. So negative 1,000 divided by negative 2.5 is indeed 400. 400 divided by negative 2.5 is negative 160. So note, because 400 is positive and the divisor 2.5 is negative, it should give you a negative quotient in 160. Negative 160 divided by negative 2.5 is positive 64. And finally, to figure out the next digit, 64 divided by negative 2.5 should be negative 128 over 5 or negative 25.6. So either notation is okay, whichever is preferable to you guys. All right, I accept both notations. All right, linear versus exponential functions. So linear functions are those function types whose succeeding elements are determined by adding, whether positive or negative, a constant to a current or previous term. Aha! So if the pattern is just adding or subtracting a particular number to get the next number, that is a linear function. Aha! That makes sense. Exponential functions, on the other hand, all right, can be determined by multiplying a particular number to a previous number to determine the succeeding term. Aha, Mr. Trusino, wait 1 second. Number 4 on the previous example says it has to be divided by negative 2.5. So how does that make it multiply? Later, we'll actually see how that works. All right? Okay, so now we're going to classify functions here. Okay, so number 1 and 3, all right, definitely both linear. Number 1, you keep adding 4, linear property. Number 3, you keep subtracting 3/4, which is like adding negative 3/4. Right? Linear property. Right? Number 2 and 4 are both exponential. Okay. Number 2 is exponential because you keep multiplying by 3. Number 4, on the other hand, is also exponential. Okay. But here, it's a bit confusing because it says we have to divide by negative 2.5. Again, we will address that issue later. All right, but for now, take note that this one is also classified as an exponential function. Later, you'll discover why it is classified as an exponential function, even though it says divide and not multiply. For some of you guys, I think you probably figured out already why it's still classified as exponential, even though it says we have to keep dividing. All right, hold your thoughts on that one though. Standard forms of functions. So as a linear function, it should follow the standard form y is equal to mx plus b. All right, the slope and intercept form. All right, now for convenience, we're only going to use a semi-standard equation form for the exponential function. In this case, we will only use the form y is equal to a m raised to the x. So the exponent x only applies to the number m. Okay, so notice that I used m for the exponential function and also the linear function. Of course, I could have used a lot of different letters here, but I decided to choose M because of the way the pattern works. All right. As I mentioned, this equation has been rewritten for convenience. All right. This is not the most common notation, but I have rewritten it so that it's very convenient in our discussion. Okay. Standard linear function graphs. Okay. Because it's a linear function, of course, you will expect that the graph will follow a line, right? So for linear functions, m, which is the slope, all right, is the number that is being added positively or negatively to a given term. Okay, so whatever you keep adding to get the next term, that is our slope. Okay, so for number 1, that is simply positive 4. But for number 3, that is negative 3/4. B is the value of y, because B is the y-intercept. All right, now remember the definition of the y-intercept. Y-intercept is the value of y when x is 0. All right, y-intercept. Thus, for number 1, we can definitely tell that the linear equation is y is equal to 4x minus 9. This one is a bit different, because if we look at number 1, negative 5, negative 1, 3, 7, 11. Where is negative 9 there? All right, it's not there. And similarly, for number 3, it says y is equal to negative 3/4 x plus 43/4. The negative 3/4, that makes sense. That is the number that you keep adding to get the next term. But 43/4, where is that? Because here I have 10. Here I have 37/4. I have 17 halves. I have 31/4. I know the next one is 7. But where is 43/4? Right? That is actually a question, all right, that you guys need to figure out on your own. Why is equation 1 written as y is equal to 4x minus 9, and why is the equation for number 3 written as y is equal to negative 3/4 x plus 43/4? Right? I did graph these two linear equations on the next slide, and hopefully the next slide will actually give you a clue if you haven't figured out why the equation is written this way. It has a minus 9 here, although the previous example did not have a minus 9. And the third one has a 43/4, even though you did not have a 43/4 in the beginning. So let's see. So here are our linear functions. The red one is for linear function of number 1, and the blue one is for linear function of number 3. Okay, so notice I've also highlighted, all right, those particular points. The green lines, all right, are indicators for what particular x values. So the first green line here is when x is equal to 1. So notice the coordinate is 1 and negative 5. The second green line is when x is 2, and so on and so forth, all the way up to x is equal to 5. Right? Because in our solution, we're supposed to figure out the 5th element or the 5th number in the series. All right? Notice, oh, look at here. It says 0 and negative 9. The negative 9 appears there. So what was the connection of the negative 9 earlier? All right? 0, negative 9, 1, negative 5, 2, negative 1, 3, 3, 4, 7, 5, 11. All right? So we can see the numbers from the first series, negative 5, negative 1, 3, 7, and 11 do show up here. All right, but it seems weird to see a negative 9 there. All right, so why is there a negative 9 there? And why is that the important number to write here in the equation? In the same manner, right, we also have the blue line, which is the line for linear equation number 3. We have 0, 10.75. Now, 10.75 is 43/4. You may check using a calculator. All right, so here I have 110, I have 2 and 9.25, I have 3 and 8.5, 4 and 7.75, and finally I have 5 and 7. So notice again the y coordinates here. 10, 9.25 is 37/4, 8.5 is 17 halves. 7.75 definitely is 31 fourths. And 7, that was the fifth number that we did figure out. Okay, so why is it 43 over 4 here and negative 9 over there? When those numbers clearly weren't in the series numbers. All right, so remember to figure it out, because once you've figured out how this goes into the equation, it makes it easier to understand the next set of logic for the exponential functions. Right, so if you'd like to if you'd like to like figure it out, you may pause the video right now, try to figure it out, and then afterwards unpause it to continue watching for exponential functions. Okay, so if you did pause it, I hope that you figured out already why it was negative 9 here and why it was 43 over 4 for equation number 3. All right, let's go to exponential functions. Standard exponential function graphs. Okay, the semi-standard exponential function, which of course we defined earlier as what we will be using as of right now, is of the form y is equal to am raised to the x. Now take note, the x is an exponent and it only applies to m. All right? Okay, in this case, m, all right, earlier was actually the slope, which was the number that you kept adding, all right, to figure out what the next number is. In this particular context, in exponential function context, m is now the number that we multiply to get the next term. A stands for the y-intercept. Aha. So in this particular context, A is also a y-intercept, which means it's a value of y when x is set to 0. For number 2, since we multiply the current or previous term by 3 to get the next term, we can see that m is equal to 3, which makes sense. If we look at number 2, 2, 6, 18, 54, 162, we do multiply by 3 to get the next term. So in this particular context, m is equal to 3 because that is the number we keep multiplying. However, the first term when x is equal to 1 is 2, which tells us that a is equal to 2/3. Why? Aha. The same question that has haunted us for linear functions is now being asked for exponential functions. How come the y-intercepts are behaving differently? Okay, so let's see number 4. Let's see if it also behaves in a different way. Number 4 might seem a bit difficult, right? But note that we get the next term by dividing by negative 2.5, right? Now, this means if we're dividing by negative 2.5, we can actually get the same answer by multiplying with the reciprocal of negative 2.5. Remember, if you are dividing a particular number with a particular divisor, it is the same result if you multiply the number with the reciprocal of the divisor. So instead of dividing by negative 2.5 or negative 5 halves, okay, for those who are more comfortable with fractional notations, okay, this is equivalent by multiplying the previous number by the reciprocal of negative 2.5. Thus, m would be equal to 1 divided by negative 2.5, the reciprocal. All right. So if you divide this, 1 divided by negative 2.5, this is negative 0.4. And of course, the reciprocal of negative 5/2, you just need to interchange the numerator with the denominator. That is negative 2/5. Knowing that the first term is negative 1,000, then A is 2,500. Oh, again, that y-intercept thing. Why is it changing? 2/3 is not there in number 2, was never mentioned there. I mean, all of those were whole numbers. It starts with a 2, and the fifth number would be a 162. And then for number 4, definitely it begins with negative 1,000, and then it ends with negative 25.6 or negative 128 over 5. So if you figured out why the y-intercept changes for the linear function, the same idea works for exponential functions. So let's now visit the graphs of this to see how the graphs look like. Okay. So the red one is the graph for number 2. I chose not to graph the two functions together because of the scaling. I mean, the first one, it starts off, the first one, the highest is 100. But the second one, the number 1 and number 4, its highest is actually 2,500. But because of the difference in the scaling, I chose to graph them differently. Notice how the y-axis are different and how the scaling is different for both graphs. But nevertheless, let's visit the points that are present here. So notice there are again those green lines. So those green lines indicate the x values. The first green line is for x is equal to 1. The second is for x is equal to 2, all the way up to x is equal to 5. So it starts off at 0.667. Now, 0.667 is actually an approximation for 2/3. So if you divide 2 by 3, you get 0.667. Here, we have 1 and 2. Next one is 2 and 6. The next one is 3 and 18. 4 and 54. All the way to 5 and 162. So notice the y values starting from here. 2, 6, 18, 54, and 162. These were the numbers in our series for number 2 of the earlier questions. All right. So if you still haven't figured out why there's a 2/3 here, all right, you should already see some connections between the x coordinates. All right. Now, let's go to number 4. Now, number 4 is an interesting graph. If you look at the graph here, notice the points actually, it's not connected. It's like jumping. So one is up here, some are above the x-axis, while the others are below the x-axis. So it keeps jumping, which is expected because the base or the base here, all right, being a negative allows the fluctuation of the signs of the resulting product after raising to a particular exponent. So we start off with 0, 2,500. So the 2,500 is this number right here. Then we have 1, negative 1,000. Okay, negative 1,000 being the first element in series number 4. We have also 2, 400. Okay, 400 was the next term. 3, negative 160, yes. 4, 64, and finally, our answer, which was 5 and negative 25.6. Okay, now negative 25.6 is, of course, negative 128/5. Right, so this concludes our first ever lesson during our online learning sessions. Right, so I will, of course, be posting a Google Docs for us to have online discussion. If you have any questions on what you have watched or read in the Google Classroom that I'll be posting. Now, the schedule for my upload is during 9 a.m. every Tuesday. Math schedule is every Tuesday. So you can expect us to upload new content every week at 9 a.m. Tuesdays. But live discussion, when I say live, that means like live chatting, right? We will all be working on a particular Google Docs. So you'll be typing questions there. All right. So to make it easy for all of us, we're actually going to all work on one Google document so that any questions posted there can be answered by me or can be answered by your fellow students. That way, we actually have great conversation as we go along. Okay. All right. So for the Google Docs, our live discussion would be from 10 to 11 during weekdays. So from 10 to 11, I will definitely be online to answer every question that you ask on those Google Docs. If you have like questions on the lesson, you may post it there. Mr. Tricino, how is that possible? Like this example. I prefer Google Docs because I will also be able to upload there maybe screenshots of handwritten solutions, because sometimes it is easy. It's easier for us to view solutions if it's handwritten as opposed to trying to like figure out special keys to denote mathematical symbols. I think it's much faster if you can just handwrite it and then just paste it over to the document. Okay, so remember the schedule. Every Tuesday at 9 a.m. I will be posting new content. Then weekdays, I will be available for our Google Docs discussion from 10 in the morning up to 11 in the morning. So if I do not finish answering the questions, let's say it was Tuesday, and then 11 a.m. struck, and I still haven't answered your question, don't worry. Come Wednesday, I will definitely go back to that question and answer them. Okay, so if you have if there would be no further clarifications, all right? So just remember to post on the Google Docs discussion. You remember to keep safe. All right, study hard. Hopefully this first day of our online learning was really good. All right, so I'll see you guys. All right, have a great day. Bye.